So I would like to thank all of the organizers for it's very nice to be back here in IHS and for putting together such a nice group of people. And I should also apologize on two points. So one is that I have it has been a number of years since I was working actively on this topic, so my memory is maybe not as fresh as it should have been otherwise. And the other one is that I was hoping to have a last week to get a little bit more into it, but then I had a cold, as you might recognize. So you have to bear with me. So I plan to focus more on the spectral properties of the membrane matrix models and discuss the difference between sort of the classical side, the quantum, and the supersymmetric matrix models that arise from the membrane. So the plan is to give a little bit more of the introduction. So we have already heard many of the talks have focused on bringing to our attention the different aspects of these models, but I think it does not hurt to point out a few extra things. And also I believe that in this audience there are several people who are not experts in this area, so I think it could be nice to understand this in more detail, and then focus around the spectrum and in particular the ground state conjecture. So this is concerning whether the lowest point of the spectrum, which turns out to cover the positive real axis, whether this the point 0 is an eigenvalue or not, whether there exists a normalizable eigenstate. And then I will discuss various approaches to the study of ground states. There have been many over the years, and I have been involved in some of these and provide some outlook. So if we recall, we're considering a bosonic membrane. So let's start with the bosonic case. So this just means that we have the embedding of a membrane in sort of world volume into space-time. And so if the picture one could keep in mind is sort of that we have, okay, this is some surface, and then we have some time dimension, which is sweeping out world volume. And so sigma is fixed. Let's fix the topology as a start, and then 2D compact manifold. And then we have the embedding coordinate functions, so x. And here I'm working in the sort of light front or light cone coordinate framework. So even though the embedding space-time is r, so 1 plus little d will be my parameter in these models, and then 1 time dimension. So d is essentially the transversal coordinates to the membrane. So we have d such embedding coordinate functions into one for each of the coordinates. And then there is this issue of writing down the Hamiltonian. So this is after having done this reduction into the light front coordinates and looking at the internal energy of the membrane. So this energy is given by this Hamiltonian function on the phase space. So we have these x coordinate functions, but also there are the conjugate momenta p. So so this is then just an integral over this fixed surface here. If you want to think of it as having, maybe there is some hole in it. And we have the momenta squared, and then there is this Poisson bracket. So you have the Poisson bracket of the coordinate functions squared to sort of provide for you the volume of this thing. And so we have essentially two Poisson structures here. One is given by the surface sigma, Here I might have set this normalization to one, this density to 1, but there's some flexibility there. And so this is one of the Poisson structures that we use, which is sort of canonically given since it's a two-dimensional surface. But then we also have the dynamical Poisson bracket. So these coordinate functions and the momenta should be canonically conjugate. So that's this Poisson bracket in the end here that have been normalized in this way. And I can say also that some of the details concerning the dimensional reduction from the full theory down to this setting, you have to sort of eliminate some constraints and so on. There have been some discussion in a paper with De Wool and Hoppe. Then we go over to the matrix context, and as we have seen, we should then replace this Poisson algebra of functions on the surface. Actually, they have also been normalized, so we have taken away essentially center of mass and so on, so that they are zero mean real valued functions, xj. And then we represent this Poisson algebra in terms of matrices. So we're then going over to an algebra of traceless, Hermitian, m/n matrices. So the tracelessness is from the zero mean and Hermitian from the real valued functions. And then it's just n is the matrix size. And then in this representation, we represent the Poisson bracket by the commutator of the matrices, and the integral on the surface goes over to the trace. And then the nice feature here is that there is a convergence, so we can essentially a little bit independently of the actual topology and so on of the surface, we can arrange a basis of our traceless Hermitian matrices such that the structure constants in this basis converges to the given one. Yes.
So if you wanted to use higher genus surfaces to parameterize your membranes, how would that show up on the right-hand side?
So then I think you would need to choose a different basis which gives you those structure constants, but maybe Jens would be the most suited to.
What we did, it was discussed earlier. So this answer is the following. There is an abstract theorem, I mean many different aspects, but one, for instance, Bordemann, Meinranken, Schlichenmeier, who proved that for any genus surface, the algebra of the matrix algebra can be taken to converge to the genus G surface. But it is not known what basis to explicitly take for higher genus surfaces. I mean, these matrices in which you get the structure constants F, A, B, C are only known for tori and spheres.
Okay.
Yeah, so there's an existence of there's a sequence of bases and thus a sequence of structure constants in those bases such that you get convergence. Okay, but the details is a bit more tricky. But the whole idea here is that it respects this representation somehow respects the symmetries, or if you want, the constraints of the theory. So we had in the original membrane theory we had the diffeomorphism invariance on the surface and actually area preserving diffeomorphisms because we want to conserve the area. And then this in the matrix model side is represented as a SUN invariance, so the special unitary because of also this area preserving constraint. So we have then the Hamiltonian, which we have seen is now a trace over sort of the momentum side of the matrices squared, and then you have the commutator squared over all the pairs of the matrices. And if you want to write this down in terms of a basis, say, of SUN, some standard basis, then you have just the sum of the momenta squared, and then we have we have the structure constants, and then so this would be the commutator squared. And then still we still have so the canonical Poisson brackets between the coordinate and momentum variables here. But now there's only finitely many of them. So that's the whole idea here, that since we have a finite dimensional system, we can then quantize this in the standard way using the Schrödinger quantization. So, so we represent this set of coordinates and momenta on square integrable functions over the corresponding dimension. So we had the d space dimensions, and then this is the matrix dimension, or the basis, the number of elements of a basis of this space. And then we represent our xj as just multiplication operators on this space. So we have expanded it in this basis Ta. And while the momenta is represented in terms of derivatives, so minus I times the derivative with respect to xj, in order to represent the the canonical commutation relations. So then our Hamiltonian that we had, the sum of p squares goes over to the Laplacian acting on this space, and then we have a scalar potential essentially, which depends on the coordinates. And I will come back to the details on this potential. But what we have here is also symmetries. So we have essentially the d-dimensional space, and the rotations may be represented within this. Essentially, the Hamiltonian commutes with such rotations, but it also commutes with rotations in the matrix space, so SUN transformations, which are then represented if you in this basis by orthogonal transformations as well. So, but what we have to remember is that we have these constraints of diffeomorphism invariance. So we still have that constraint which we have to implement. So actually, the physical Hilbert space is not the whole space here, but rather this is where I wrote the sort of bosonic Hilbert space physical, which is then the SUN invariant states. So the SUN, so the generators of the SUN symmetry can be written in terms of this basis with the structure constant like this. And that acting on our states should be 0. So that's how we implement the constraints. And this is sort of just amounts to the standard Dirac constraint quantization procedure, that we still have some constraints, so we will look for to solve those constraints on the quantum side.
This is a constraint? This one?
This one is a constraint, yes. So
First class or second class?
this is at this point I don't remember. Yeah, it could be second class at this point. So yeah, but you have to. This is probably written in this paper. Okay. So then we have this complication of supersymmetry, if we want to consider the supersymmetric membrane. So the idea is to somehow add spin degrees of freedom and obtain a supersymmetric theory. So, so I will say just something briefly about supersymmetric quantum mechanics, because it's not the full, supersymmetric quantum field theory here, but it's really a reduced thing into the quantum mechanics. So then it can be more simply stated. So essentially, a supersymmetric quantum mechanics, you can think of having a couple of different objects. So one thing is there's a Hilbert space, there's a grading operator K, there's a Hamiltonian, and then there's supercharges, so supercharge operators. So you have a Hilbert space. The grading operator is just an operator. A boundary operator is going to 1, so you can sort of split the Hilbert space into a positive and negative part, or the eigenspaces of this, and you can term this the even sector and the odd sector. And then this Hamiltonian operator, it should be even with respect to this grading, so it should map even to even and odd to odd, and it should be a self-adjoint operator. But then you have these supercharge operators, Qj, and if there are n, the curly n of them, that we say that there's an n extended supersymmetry. These should be odd operators, so they are mapping the even to the odd and the odd to the even. So they're sort of interchanging these spaces. And they should satisfy essentially this Clifford type algebra that so okay, a square of an Qj should be the Hamiltonian, but they should also anti-commute. So this is the definition of this supersymmetric quantum mechanics, and some nice properties of that are implied just by this structure is that your Hamiltonian will necessarily be non-negative operator because it's the square of, okay, I should say these are, in this formulation, these are self-adjoint operators also. So the spectrum of the Hamiltonian has to be on the positive real line. Then there is a pairing between the eigenstates of the Hamiltonian. So if you actually have an eigenstate with a positive energy of the Hamiltonian, so say that you have it, and you can sort of, use this splitting. So you can say that you have an even state, for instance, with positive energy. Then by just acting on it with the supercharge, we get to the odd sector. So you would have an eigenstate with the same eigenvalue E on that sector. So there's always a pairing for the higher energy eigenvalues, but not necessarily on the zero energy sector. Because then you would annihilate the state by acting on Q. So, so this is used, for instance, in index theorems and so on to spot whether there is a zero energy state or not. Okay, and then in this in the supersymmetric formulation, what we want to do is somehow to, instead of having SOD as the rotation group symmetry, we want to have a spin D represented non-trivially in our space. So we're considering actually representations, both sort of spin representations with respect to the RD space, but also with respect to the sort of the matrix space. And these should be represented as some bounded operators on some Fock space, or some, the Hilbert space of the model. So we then have to go to Clifford algebras to construct such representations. So starting with the d-dimensional space, and we're looking at corresponding Clifford algebra over d dimensions. So say gamma matrices satisfying the anti-commutation relations. And then you take an irreducible representation for these matrices, or just a certain matrix size. And I call this n d. So this depends on the dimension, and there is a certain natural irreducible representation here. Then you construct over this space that you got, you then sort of couple that to these matrices, to the matrix degrees of freedom, and then you construct a Clifford algebra on top of that space. So then we go up in dimension a bit more. And then you consider the irreducible representations of that algebra, and that will be even bigger. So then it's the dimension is 2 to the, and then it's essentially this this dimension here, nd times n squared minus 1, and then half of that. And we will see explicitly how you construct these things, this in one way.
Really a real representation of the gamma matrix?
Yeah, so here we consider actually a complex representation, but you can ask whether you should want a real or a complex one. But typically at this, so here it's the first stage is so it depends a bit what kind of structure we can get. So I will come to this soon, but so this real representation in certain dimensions, this turns out to be actually a complex or a quaternionic representation, and then you can use that. But on this stage, you can also ask, should you have a real or not? But let's think of just the complex case in this case. Otherwise, it would be more complicated here. So what happens in this picture is that adding to our bosonic Hamiltonian, so the kinetic energy essentially plus the scalar potential, we add these so spin degrees of freedom, or these fermionic operators the theta, and they are coming with linearly in the coordinates x. The rest is just these sort of structural constants. And then it turns out that you can write down a set of supercharges. So the number of supersymmetries essentially is this dimension here. So you have a linear in momenta and then quadratic in the x's, and then coupled to these fermionic variables. And then it turns out that for certain dimensions, these satisfy this supersymmetry algebra. That the anticommutator of such supercharges gives you the Hamiltonian, but there will be an additional part here. But it turns out that on the physical Hilbert space, so this is just the generators of SUN. So on the physical Hilbert space, this piece vanishes. So you have it closes up to this supersymmetry algebra. So in order to understand this requirement, one needs to know a little bit more about Clifford algebras and so on. But I don't have so much time to get into it, but let me just, I think it's useful to have sort of this table. So this is the dimension, this RD, and then you consider the corresponding Clifford algebra. And these are well known to be just essentially matrix algebras or a sum of two matrix algebras. But the matrices are, have a real or complex or quaternionic structure. So this is just the dimension of the Euclidean space that we construct this Clifford algebra over. And then this is the dimension of the irreducible representation of the Clifford algebra, and this you can read off from this side. Then I have essentially just written what sort of the structure is in these spaces, whether there is an additional complex or quaternionic structure. And then on the right-hand side here is what happens when you act, essentially how can spin D be represented on these spaces. And then there is an additional splitting into either you have just essentially an irreducible representation, or it splits into two either different or the same representations. So actually you can see here that the special dimensions where you have these this supersymmetry is the case. So for my label of D here, it's the 2, 3, 5, and 9 cases. So this is what I've marked with the arrows here. And it turns out, so in the 2 case, essentially the structure is real, but in the 3 case, the structure is complex, and you can use that. And also in the 5-dimensional case, there's a quaternionic structure, which you also can use. While in the highest dimensional case, which is of the most interest, is essentially a real structure, but it turns out that there's sort of octonionic features in this case also. I have also indicated this one here, which is somehow a degenerate case, the 1-dimensional case. So so this is somehow, if you want some kind of 0-dimensional thing, you know. So this is again related to the fact that you have essentially the norm division algebras are the real, complex, quaternionic, and octonionic ones. And this is sort of the same thing which appears here, which has to do with Clifford algebras. Okay, so I might come back to this table. So now our full Hilbert space is then the bosonic one times the fermionic Fock space, where we have represented these Clifford algebras. And then again, there's a physical Hilbert space, which where these constraints vanish. But now it's not only that bosonic sector, but there's also the fermionic part here. So that's imposed as a constraint that we should be in the kernel of these operators. But then you still have also a symmetry, sort of a rotation or spin D symmetry, which is then essentially rotation among the coordinates, and then also rotation on these Clifford algebras or on the fermionic Fock space. So what we'd like to emphasize here is also that how we can construct these Fock space representations. So essentially the one way, which was used by De Witt, Hoppe, and Nicolai, is to essentially you pair up. You have to, so you given these thetas, this Clifford algebra, you can sort of pair them up to construct creation and annihilation operators. So one way is just sort of, okay, you take the first half and the second half and pair those up, and then you have essentially creation annihilation fermionic operators satisfying canonical algebra like this. And what has been done essentially is to split the space. So along with this pairing, you use a splitting of the d-dimensional space into d minus 2 variables, and then the last two you use as a sort of complex variable. We can take the real and the imaginary part of that. So I've here written x prime is sort of the first set of variables here, and then z is the pairing of the two last variables, d minus 1 and d. And if you do that, this sort of goes well together, and you can write down the Hamiltonian in terms of these creation annihilation operators. So then there will be a part which involves these first variables here, and so big gamma is sort of the reduction of these gamma matrices in terms of this splitting. And then you have the last part is so this first part sort of preserves the fermion number, but in the last two parts you have a raising of 2 or lowering of 2 fermions. So in this sense, the whole operator will sort of mix the fermionic sectors. But there is this alternative in 3 and 5 dimensions, which I'm not sure how much it has been discussed. Okay, it's also been used by Claudeson and Halpern, and then discussed this a little bit in my thesis, that in these special cases, since you have this complex or quaternionic structure, you can use that pairing, which gives you a more sort of canonical pairing of the fermions. So that in that case, your Hamiltonian can be written, so using this other pairing, you have essentially, so your Hamiltonian is then the bosonic, and then you have a piece which conserves the fermion number. And then the SUN and the spin D generators are also sort of preserving fermion number. Then there was this degenerate model, which essentially, so it's the one-dimensional case, which essentially is just a free Laplacian acting on the matrix degrees of freedom, and then there's a piece which vanishes on the physical Hilbert space. So one way to the corresponding supercharge. So there's only one supercharge in this case. It's essentially just a theta times derivative. So this is like a Dirac operator, and its square is this Hamiltonian on the physical Hilbert space. But there's also here an alternative. So either you sort of work with this, or you construct what you can call somehow cohomological version, which is so there's a way to also introduce fermionic creation annihilation operators, and then you have a Q which is not self-adjoint, but you also have a Q star such that they sort of close up this supersymmetry algebra. Let me not spend too much on that. So now we come to the question of what about the spectra of this model. So we had the classical side, and just the membrane or its regularized version, and then we have the quantum regularized membrane and the quantum supermembrane. And one way to understand these differences is using toy models, which has been very fruitful. So if we start with the classical model, we have this Hamiltonian again, the trace of these momenta, and then the potential, which we should note is a non-negative potential here. And a toy model that you can keep in mind, so if maybe I can write it here. So essentially we have a toy model potential which only depends on 2 variables, so it's in R2, and it's x squared, y squared. So the feature here is that there's certain flat directions. So if we think about this, toy model, we have this in the xy plane. Then along the coordinate axis, the potential vanishes, but then it somehow increases rapidly transversally to these cases. So this is indeed the picture that arises here, that in this matrix model potential, you have vanishing directions where all of these matrices are commuting. So it's essentially such a asymptotic direction. So you can really go out to infinity while the potential vanishes. But the important feature is that while you move in such a potential valley, the valley also gets steeper and steeper in this in the transverse direction. So because of this narrowing, it turns out that you can actually there's a difference on the quantum side. But if you just consider moving with a fixed energy in this potential well, then you can indeed escape in the well to infinity. So in this sense, it's an unconfined potential. So on the quantum side, so we are then considering this Schrödinger operator, essentially the Laplacian here, plus this scalar potential. And then again, it's both of these operators non-negative, but the important feature is this narrowing of the potential valleys here. So we can again consider this toy model Hamiltonian. So on the quantum side here, so this is the bosonic toy model, which is then just the Laplacian in the 2 dimensions, plus this this potential. And here you can use essentially this illustration, but it's a little bit more complicated on the matrix side, but essentially the same kind of computation. That so considering this operator, you use what is sort of happening along the valleys here to bound this operator from below by something which has a discrete spectrum. So what you can do is sort of take half of your momenta here, and you sort of you split your potential into two pieces, half and a half, and then you take also half of the x momentum, put it here, half of the y momentum, put it there, and then you consider these two parts here separately. So this, if you recognize it, it's just like a harmonic oscillator in the x variable with a frequency y here. So this is just bounded from below by the sort of zero point energy, which is then the frequency y. And the same thing here, it's just symmetric in x and y. So here we have somehow used that in such a valley, there will be some kind of 0 point energy due to the narrowing of this valley here, which then depends on how far out you are in the valley, essentially. So bounding from below with these parts, you get in total an operator which has a potential which goes to infinity in all directions. Because of this, it has compact resolvent, and so it has a discrete spectrum. And also it cannot have a zero eigenvalue. You can see this, for instance, by Sobolev inequality or something like this. So this is the interesting feature here, that we, on the quantum side, we get actually a discrete spectrum for this operator. The same thing goes through, as I mentioned, on the with this more complicated potential. So essentially you can parameterize this in a smart way to see this. But then everything changes on the supersymmetric side. So we had this bosonic operator, which we now know has a discrete spectrum. But then what happened here was that we added this essentially a matrix piece here. It's linear in the coordinates, but then there's this matrix here also. What we already know is, due to the supersymmetry, that this operator is the square of something. some self-adjoint operator. So we know already that even though we added this part which is not definite, it still is a non-negative operator. And actually it's really important, so for the supersymmetry it turns out then you will have a matching between, you know, you cannot just change any of these terms with some coupling constant or something, because it has to match up. There is also in this case a toy model. So essentially it's this bosonic toy model with an additional piece. So maybe it's useful to write it down. So this is the supersymmetric toy model. It's essentially the same thing we had on the R2. Then there is the identity matrix here, and then you have a part which you can write. So this depends on your taste, but one way to write it down is in terms of two Pauli matrices. So this operator is acting on, so it's L2 on R2 with values in C2 actually. So you have the Pauli matrices acting here. Yes.
Yeah, I'm sort of confused why you say minus square root of x. Oh, okay.
Yeah, okay, so
Minus.
exactly. So I'm looking at this piece here, which is sort of, this is the one which is linear in the coordinates times a matrix. And if I square that, so the square of this part is just x squared plus y squared due to the Pauli matrices. So so that means that this operator is bounded from below by at least the negative square root of that. So this is what you can use on this side then. That whatever it is, okay, it can become arbitrarily negative, but essentially if you go along a potential value, so if y is 0 and you go along x here, then you have just minus the absolute value of x along this value. And this matches up exactly with this corresponding harmonic oscillator 0-point energy. So what happens is that there is this exact balancing out between the 0-point energy of that oscillator and this fermionic operator here. So it turns out now that this changes the spectrum again. So it's no longer a discrete spectrum, but it's rather a continuous spectrum on the positive real line for this operator. It of course depends on which operator we consider, but this toy model has the same essentially features as the real matrix models. So it turns out that also in the full matrix models, you can prove that this corresponding operator has an essential spectrum from 0 to plus infinity. So what you do is essentially to use this fact that so on the fermionic side you put yourself in where this is as small as it can be, and in the bosonic side you take a state such that this is the smallest it can be, and that there will be this balance between these. And essentially you can construct then a sequence of states which sort of get pushed out into this valley, and in this sense a sequence of while sequence of states. So you can prove that there exists a sequence of smooth and rapidly decaying states. I think maybe you can even, maybe not compactly support, well, you can take them compactly supported and normalized such that for any lambda greater than or equal to 0, the Hamiltonian minus that acting on these states goes to 0. So this means that this point lambda is in the spectrum.
The theorem is for the full...
This is for the full, exactly. So this was in De Witt, Lüscher, and Nicolai, where they also used this toy model to illustrate the point. So in the toy model case, as I said, this was so psi should correspond to putting yourself in the lowest energy here, and then this phi is essentially the eigenstate in the transverse direction, and then the psi is used to as a cutoff to move into the valley.
Why does it mean that the membrane is unstable?
So in some sense it means that it costs zero energy to just deform everything. You can move into this valley with zero energy cost. So in that in that sense that so what it means in these valleys, if I understand correctly, is somehow you can form spikes of your membrane, and so these spikes somehow you cannot see. Somehow the uncertainty principle is not there to stop you from such spikes forming. So there is somehow, from the fermionic degrees of freedom, there is an extra, it allows you to somehow fluctuate with spikes. But I think in some interpretations, then this is used as an advantage, that you can somehow, if you have a membrane, it can somehow form a small tube or a spike, and then it can maybe form a new membrane in some other section, and it's just connected by this little tube. So somehow you're allowed to change the number of membranes and these things, that there's some kind of second quantized interpretation there, that it can fluctuate in the components and the topology and everything. Okay, so then there was this conjecture concerning the existence of ground state. So we should think about the case now that, so concerning the spectrum of our operator, so we know that in all of these cases, the supersymmetric cases, you have a spectrum which is on the positive real axis. So this is the spectrum of the supersymmetric Hamiltonian. And the question is really, what about the point 0 in the spectrum? Is somehow so whether there's some stability in the sense that that you will have a lowest energy state where everything can somehow boil down to. Or if it's just, if there is no normalizable ground state there, that somehow tells you that things are leaking out to infinity. There's no stability. So the conjecture was that in the highest dimensional case, there should be a normalizable zero energy ground state. So this point should be an eigenvalue, and also that there's a uniqueness there, so that there's only one such state. While in the lower dimensional models, there should be no normalizable zero energy state for any matrix size. And also this statement was for all matrix sizes.
By the way, you separated the center of mass motion. The thing is...
Yes, so this is now...
So if I have a k square equals 0 ground state, I would not see it. I mean, if this is a massless ground state, it cannot be... I cannot go to the center of mass, right? Is it excluded by the formalism?
No, I think that's just... but I think that problem probably trivializes the center of mass problem. Is somehow, you have somehow separated these things. So I think this, on the center of mass side, this is probably just like a particle.
Gauges for the string, when one quantizes the string, if you do it badly, you eliminate the massless concept. But anyway,
Okay.
we can discuss
Yeah.
that separately.
Okay, but yes, let's discuss it. So. So this conjecture is then supported by various evidence. So in the case, the lowest, sort of the simplest case among the full matrix models, so the two-dimensional and 2x2 matrices, there is a proof by contradiction due to Jörg Fröhlich and Jens Hoppe.
So proof that there does not exist.
That there does not exist such ground state. And if I understand this correctly, it's again has to do with somehow the size of the or that yeah, we will come to this, but there's sort of the geometry involved here, and whether there's, you know, whether these states are essentially decaying fast enough at infinity. And this question was then addressed, I guess it was discussed somehow in Halpern and Schwarz, but then Fröhlich, Graf, Hassler, Hoppe, and Yau considered the asymptotics also in the n=2 case, essentially studying what happens along these valleys and looking at the equation. I think that this is zero energy state with respect to the supercharge. You can then see essentially what are the decay properties of such a state. You know, how is it decaying as you go out to infinity? So the question is it decaying fast enough to be normalizable, or does it sort of, maybe it does not even decay, it could also blow up, or just stay constant, or, you know, and there's then you have to be you have to sort of know also the size of these valleys and so on. So there's a lot of interesting geometry in this. Then I guess Pellegrini will tell us more about the Witten index approach. However, I should point out that in these models, because of this spectrum being continuous and you know, various difficulties of non-compactness here, one has to be careful when you make the index computations. So you cannot just assume that you have a discrete spectrum and work on that. So what I would like to point out, though, is the existence of embedded eigenvalues actually in the spectrum. So it turns out, using this, the way we can define the model, choosing our fermions. So in the 3 and 5 case, when we chose the fermions the way we did in this slide. So since we could write down the Hamiltonian where the fermion number is preserved, then we can work on a sector where essentially you have 0 fermions. So on that sector, this Hamiltonian just reduces to the bosonic Hamiltonian. So in these cases, due to the existence of this complex structure, you can actually sort of just split. So you use this structure to somehow split the Hilbert space into different sectors of fermion numbers. And on one of those sectors, the Hamiltonian is just the ordinary bosonic Hamiltonian. And we know that the bosonic Hamiltonian has a discrete spectrum. So in these cases, there indeed exist points in the spectrum which come from the bosonic Hamiltonian. So that proves that there exist embedded eigenvalues in those models. But this was in these cases, the 3 and 5. So the problem is in the say 2 and 9 dimensional case, we do not have this canonical structure, and indeed, essentially the best we can do is to have these non-fermion number conserving terms, which then mess up the whole picture somehow. So it's difficult to see whether there is such a reduction in that case. So that was what I'd like to point out here, that we can on the right Fock space sector we have the same Hamiltonian here. So another thing which is important to point out is in the 3-dimensional case, you do have you can write down states which are 0 energy states, but they are certainly not normalizable. So essentially, what you can use in this case, that that the supercharges can actually be written as essentially a Dirac operator, but then conjugated with a superpotential, essentially, which is of a cubic type. So you take essentially these. So in the 3-dimensional case, you have also more canonical pairing up between all these essentially form a volume form in this in the 3 dimensions, taking these 3 matrices, and so you use the antisymmetric tensor in 3 dimensions, and then the structure constants, so forming a real valued function. So indeed, this also has some properties like certain valleys where it's 0, certain directions where it's actually blowing up positively and then blowing up on the negative side. So it's indefinite. But if you just write formally a state where you have essentially 0 fermions and then you multiply by this function, then this is it's a smooth function, and it's in the kernel of this of the supercharge, but it's not in the Hilbert space because of the indefiniteness of this. And then you have a similar state if you just switch the sign and you take the full fermionic thing. So in this, due to the structure, there exist such states, but they are certainly not normalizable, and they cannot be made normalizable just by changing. You have to really change the inner product of your Hilbert space a lot, having exponential decay in order to accommodate such states. And also in the one-dimensional case, there is essentially this you can think of as a plane wave model, or the supercharge is just essentially a derivative times a fermionic variable. So again, you can just take states which are constant with respect to that. So either you take 0 fermions or full number of fermions, and then acting with the derivative, it's just 0. So, but this is again, it's a constant, so it's not in the Hilbert space, but it's better than this case, because then it's constant. So if you just change your inner product a little bit, you can somehow accommodate for it. So this is an interesting question, whether one should somehow change the normalization and play around with whether these types of states should be included or not. Okay, so I will not go into so much of the detail on these different approaches, but essentially one approach is by construction. So you write down recursive equations on the different sort of expanding. So one approach is to expand, essentially Taylor expand the ground state around the point x equals 0, and see how you can relate the higher order terms to each other. So this has been sort of fruitful, that we can find a unique state due to all the symmetries and everything. You can find a unique value for the ground state at the point 0, and then also I think to the first order, but then there might be more possibilities if you go up in order. Another approach has been to deform the model. So what you can do is somehow to single out some of the directions and make a deformation, and then arrive at a different model which still has the same complicated spectrum, a continuous spectrum, but it has somehow reduced in complexity on some other aspects. So this might be more amenable to computations. And another approach is to somehow average with respect to symmetries. So again, you can view the model in a certain direction, or understand a certain region or selection of the coordinates as essentially also a harmonic oscillator type of problem. And then it turns out that if you take this operator, which is then defined in this direction, and you somehow average it over the directions, you will find the full operator. So the hope is to be able to use some averaging techniques to arrive at the model. And then another approach has been to try to investigate this case, whether the 0 NU states just are not in the Hilbert space, but maybe they're sort of weakly in the Hilbert space, so that if you just change your normalization a bit, or if you allow for a slower decay, or either just having constant functions or a slow decay, that you might then spot these states and can somehow understand them from that perspective. That if you, that perhaps this is just a dimensional issue, or that the decay is somehow there because of the geometry, and then so maybe there's both in the 2-dimensional case and in the 9-dimensional case there could be a ground state, but it could turn out that it's in the higher dimensional case that the decay is fast enough. Okay, so maybe I just flash some things here. So this concerned the construction by recursive methods, essentially expanding the state to higher orders in the coordinates, and then considering the various conditions arising from it being a zero energy state. And then and you can find that in the 9-dimensional case, with only, well, n matrix size is 2, then you can understand this, essentially the value at the origin due to symmetry. So it has to be a certain combination of states arising from the different representations here. We'll not go into the detail of this. And also Mikishita and Chechilevsky studied the higher orders for this problem. The deformation case, so essentially it's a little bit related to this what happened in the 3-dimensional case, that you somehow consider a cubic superpotential, if you want, and then where we somehow we single out some directions, sort of say the last 2 directions, 8 and 9, and also the indices 8 and 16 in the Clifford algebra, and then somehow you can, using that those choices you can write down something which is nice, and then you can somehow deform your model with respect to this choice, and then you end up with so there's a deformation parameter mu, and you end up with a Hamiltonian which then depends on this mu, and in the case that mu is equal to 1, some of these terms drop out, and you have something which you can which is in some sense simpler, but you can still prove that this deformed thing also has the continuous spectrum. Then there is the averaging. I will maybe not say so much about this. What I can say, so I have 3 minutes. Okay. So maybe I can say a little bit about this weighted approach. So as I mentioned, the asymptotic analysis suggests to allow for more slowly decaying ground states. So we saw already in the d equals 1 this sort of degenerate model in some sense. There was this ground state which is just constant. So so the question is, okay, maybe it's just that it's not decaying fast enough. So if we change the Hilbert space a bit, and we can somehow accommodate for such states. So here I change it by adding a weight. So it's the original space, so d rd times n squared minus 1, with values in the formula Fock space, but then I change the measure here a bit. So I take this function rho alpha, which is essentially just something which is decaying as x to the minus alpha. So alpha is some weight parameter that can play with. So in this, so the new Hilbert space is just related to the old one with this function rho alpha. So then we can define a Hamiltonian with respect to the new space, so H alpha, but we define it just using the old quadratic form. So essentially, it's still Q times the Q acting on psi in the old norm. And then, so essentially, you define this as an operator. Just say you start with the smooth functions with compact support, and then you take this is a non-negative form, so then you can take the corresponding Friedrich extension here. but then there is an interesting sort of ground state correspondence here. So say that we had a state which is a ground. So if it was a ground state of the original problem, so it's in the original Hilbert space and it's a zero eigenfunction of the Hamiltonian H. But then since this deformed or this weighted Hilbert space, it's just bigger. You allow for more things here. So then it will also be in that space, and it will, because it's it's a zero eigenfunction here, so it's annihilated by Q. So it's indeed also annihilated on this side. So any ground state of the original problem is also a ground state of the weighted problem. But on the other hand, if you have a ground state of the weighted problem, then you can you know that this is annihilated by Q, and you can use essentially elliptic regularity in these things so that you can conclude that this is actually a smooth function and it's annihilated by Q. So, okay, and it's also in that weighted space. But it could be, so you have essentially everything you want, but it might not just be in the Hilbert space. So it's a useful thing to look at this space instead to see if there's just some weakly bound states somehow in this problem. So and then what you can use is certain spectral relation between the problems. So if you want to see, study the spectrum of the weighted problem, it's the same as studying the spectrum of the original problem, where you deform the Hamiltonian by, say, lambda times this function rho alpha. So essentially, if you want to see, to understand whether this has a discrete spectrum, then you just have to sort of look at the negative eigenvalues of this problem. And and also the question whether there is a zero energy ground state for the weighted problem is the same as whether this original Hamiltonian has a negative eigenvalue when you deform it in this way. So you throw in a negative potential which has this decay, so x to the minus alpha at infinity, and you ask if there is always a negative eigenvalue there, then it means that this weighted problem also has a ground state, a normalizable ground state. So then you can sort of use spectral theory for these operators and so on. So what I did was to look at the toy model again, so this one, and apply this procedure. And I find that if the weight is large enough, so if the decay is fast enough, so alpha bigger than 2, then indeed this problem, the number of negative eigenvalues is bounded by a constant. So this means that in this picture that there is a discrete spectrum for this model. Okay, so maybe I can sorry. This,
I mean,
yeah.
thumbs up, but you can just
So I wrap up. Maybe I can just say that in this weighted picture, you can consider essentially a weighted index to sort of try to count how many more states do you get in the weighted case than in the original case. So that's one possible approach. So then there's just this final slide. As I mentioned, one can continue to construct the ground state to higher orders around the origin. Study this deformed operator. There's also the question of averaging of eigenstates. So what I have not proceeded yet with this approach to compute the weighted index for the toy model and in the matrix models. That would be interesting as well. And then we saw that there are embedded eigenvalues in certain dimensions. But what about the 2- and 9-dimensional case? And at least in the 2-dimensional case, I think there is some kind of reduction you can make also with respect to symmetries, so that you can, in some cases, you can find. I think you can, in the 2-dimensional case, also discover a sort of a sector of the Hilbert space where you have a discrete spectrum. So thank you very much.
Thank you.
Yes.
Yeah, just a comment because it happened to be the end of your talk. This d equals 2 case. I don't remember so there is a paper by 3 former Soviet Union.
Yeah.
One of them is the mother. Where's Antal? Antal? The mother of the woman who is faculty in Brown.
Yeah.
What's her name? Arafeva? Right. So there is I don't remember the time, but a nice paper about embedded eigenvalues in d equals 2.
Yeah, this is exactly the one I was thinking of. So Arefeva, Koshelev, and Medvedev.
Ah, yeah, right. You remember Medvedev.
Any questions, comments? Yes.
But so this was very nice and a lot of information. So what is the final message? Are you saying that this waiting could allow to find finally interesting ground states weakly decaying? I wonder
Yes.
because I got lost at the end.
Yeah.
What is the main message?
Yeah, so exactly the main message is that things depend on the dimension somehow, and it could just be that even if there is no state, it could still be just that it's not normalized. There is a state which is somehow decaying, but it's not. Yeah, it's weak, just weakly decaying. Yeah, so then maybe you can compare the 2 and the 9-dimensional cases. So I think both in the, I would somehow suspect, but I don't know exactly what to ground it on, but that both in the 2-dimensional and the 9-dimensional case there is such a weak ground state, but that in the 9-dimensional case it's not only a weak state, but it's also normalizable with respect to original Hilbert space.
For the zero energy ground.
A zero energy state.
And that would also be embedded in still the continuous spectrum of the weak Nicolai.
Yes, it will. It's just here in the in the end point of the spectrum.
One more question?
So, physics-wise, what's the message? We have a center of mass motion that is just inertial, I guess. And is it crucial to have a ground state, or is it not crucial, or what? What's the physics message?
So this possibly someone else should respond to, but I think so I'm not sure exactly why you want to have a certain or what the motivation is to insist on a certain Hilbert space, or if you have some interpretation, if it turns out that your ground state is just not, it's just barely normalizable somehow. That maybe you still have an interesting interpretation of it.
Does it mean that there is, for example, a continuous mass spectrum?
That one, I think, is more interpreted in terms of this case that you can deform the membrane, that you have these, I don't know, these spikes and tubes and so on. As I understand it, this continuous spectrum indicates that you can easily move between different configurations. But then I don't know exactly what, if there's embedded eigenvalues, this is somehow stable, more stable, but it seems it can still deform. I think what you need in the end is really to just split up the Hilbert space into the different sectors, and so you have some of these, so on perhaps on the, so we have the SUN symmetry, which is actually not just a symmetry but just a constraint. So everything should be there. But then we have the spin D, and that's not a constraint but a symmetry. But there's also the part of the conjecture is also what about the symmetry of the ground state. So I think it is known that it should be, a ground state should be spin D symmetric somehow. So I think you can, if you split the whole Hilbert space down into different sectors with respect to the symmetry, then somehow then you would. There's also a question, whether these spiky states, or whether these states you use to prove the continuous spectrum, maybe they are not respecting the symmetry actually. So maybe that's just a sector which you can remove
Maybe
completely.
last Jens.
So
say something.
BFSS wanted the ground state and claimed the ground state for some duality reasons, but maybe Pilgin has the best comment. You know these
Yeah,
things.
although we motivated here as a dynamic, regularized dynamics of membrane, this has also appears. It is essentially the same thing, but in the so-called M theory hypothesis, there is an 11-dimensional theory that reduced to 10-dimensional string theory, and there is so-called Kaluza-Klein mode, momentum mode all along this compact circle. So this n, in case of SUN, n by n case, this unique state you are looking for is exactly this Kaluza-Klein particle. So this conjecture, not only n equals 16 supercharged, but 8 supercharged, 4 supercharged, come from essentially M theory and type 2 superstring compactification. So there is a large number of physics ideas that goes into this conjecture.
Maybe we thank our speaker and then continue.